Hi everyone, I'm Leo Tscata, a postdoc fellow at University of Nevada, Las Vegas. On behalf of LIGO-Virgo-KAGRA collaboration, I'm happy to welcome you to second in the webinar series describing the fourth update of Gravitational-Wave Transient Catalog, as known as GWTC-4. Today in particular will be a highlight in the series because we're going to hear about the main results of the recent observation. So I would like to introduce Daniel Williams, who is going to lead the webinar going forward. So Daniel, if you're ready, please take it away.
Thanks very much, Leo. So yes, welcome to this today's webinar where we'll be talking about GWTC 4.0, updating the Gravitational-Wave Transient Catalog with observations from the first part of the fourth LIGO-Virgo-KAGRA observing run. So this is describing a paper which you may have spotted already, which arrived on the archive back in October 2025, and which has now made its way through its publication journey and should be appearing in print in the very near future. So it's our pleasure to come and talk to you today in this webinar about these results from the first part of the fourth observing run. Just before I move on to talk more about the results themselves and introduce the rest of the panel, I wanted to quickly advertise that next week, the final in the series of these three webinars discussing GWTC 4.0 will be coming up, which describes the methods which go into producing these analyses. So we've already had the introduction section, and then the methods next week, and today the results. And this is just a slightly new way which we are going about putting together these catalog papers, where we have started to split the introductory material, the methods material, and then the results into separate publications, just to prevent them becoming unmanageably large. So today we're going to have three principal speakers during the webinar. That is myself, based at the University of Glasgow, to introduce you all. So in fact, my time talking to you during this seminar is rapidly coming to conclusion, as I'm going to hand over to Amanda Baylor, who is at the University of Wisconsin-Milwaukee, who's going to give an overview of the results and the search results from GWTC 4.0. And then we'll hand to Lucy-Anne Thomas, who's based at the California Institute of Technology, who will talk in more depth about the source properties of the candidates which are identified in the new catalog update. In addition, when we come to taking questions from any of you who are joining us today, we also have Cody Messick, who will be joining us from the University of Wisconsin-Milwaukee, who is a specialist on gravitational wave searches, and Zach Yarborough from Louisiana State, who will be here to help field any questions about detector characterization and any glitch or noise events which exist in the data which we analyzed. So without further ado, I'm going to hand directly over to Amanda to introduce the results, the things which I'm sure you are all here and excited to hear about. So Amanda, over to you.
Okay, great. Thanks, Daniel, for that nice introduction. So my name's Amanda Baylor. I'm a PhD candidate at the University of Wisconsin-Milwaukee, and I had the pleasure of helping to work on this paper. I'm coming from the searches side as a search expert, and I'll be talking to you today about a results overview of GWTC 4.0. Next slide, please. So in this publication, we have 128 new candidate gravitational wave observations, and these are all from the first part of the fourth observing run, which we call O4a. Next slide, please. So that brings our total so far from observing run 101 to observing run 4a to a total of 218. So the addition of GWTC4 more than doubles the size of our catalog. Next slide, please. We also take the 86 more significant candidates and perform what we call full parameter estimation on them. Parameter estimation is where we do further analysis to better analyze the properties of these systems, and Lucy will be talking to us more about that later. Next slide, please. So I have to give some special shout outs to events which are featured in this paper. The first one being GW 231123. And just to explain the naming convention again, GW stands for gravitational wave. So we add that prefix to all of our events. The first two numbers are the year, so 2023. The second two numbers are the month, so 11, that's November. And then the last two numbers are the day, 23. So this was detected on November 23rd, 2023. Then following the underscore is the time in UTC, which we detected the event. So the first two numbers are representing the hour, so hour 13, and then minute 54 and seconds 30. So we might get multiple events in one day. It's helpful to be able to distinguish them by their UTC time or the time they were detected. So GW231123 is the most massive event we've seen so far in any of the catalogs, and this was also published as a special event paper by itself. The masses top out at a total mass of around 236 solar masses. And then the next two that I want to mention are the two new neutron star black hole candidates, so 230518 and 230529. Then we also have within the catalog itself the highest spin of our new candidates, which belongs to GW231028. And then the loudest signal to noise ratio of our new candidates belongs to 230814. And signal to noise ratio is basically just the strength of the signal compared to the strength of the noise. A higher SNR means a louder, more significant detection. Now, this event had an SNR of 42.1, and before this, the previous record holder was actually GW170817 with an SNR of 32.4. So this was a pretty significant increase. But then we also published a special event paper on an event called GW250114, which had a signal to noise ratio of about 80. And that came out in September of last year. And that was an event from O4b. So that will be in future catalogs like GWTC5. Next slide, please. So what did we actually expect going into O4 in general? Well, we expected to have an 18-month duration. Next. But O4 is now a bit longer. It's actually from May 2023 to November of 2025, which is 30 months. So this was a significant increase in the duration that we spent observing. Next. And we also expected the Livingston and LIGO-Hanford observatories to hover around 160 to 190 megaparsecs in their sensitivity range. And this paper includes detections from the LIGO-Hanford and LIGO-Livingston observatories because this was in O4a. KAGRA did join at the beginning of O4, but collected data until about June of 2023. And the data is not included here because it's just much less sensitive than the two LIGO detectors. And Virgo did not join for this period. Next, please. And we also detected 126 binary black holes in O4a alone. So we expected between 35 and 168, but already we have a substantial amount of binary black hole candidates just in the first part of the fourth observing run. Next, please. So what did our detection frequency of new candidates look like? Well, here on the horizontal axis at the bottom, we have the week number. So O4a was 33 weeks long. So there are 33 columns here. And on the y-axis or the vertical axis is Monday through Sunday. So that's the day of the week. And the blue squares represent the number of detections that we had on a given day during that week. So you can see we have anywhere from 0 to 3, maximum being 3 per day or on a given day. And on average, we saw that we got at least one event every 3 days or so. So that's pretty good. And sometimes we go a whole week when only see one event, but there are no weeks here where we saw no events. So we had a pretty good detection rate during O4a. Next, please. So what does our scorecard look like from O1 to O4 so far? Well, you can see the addition of GWTC4 adds 126 binary black hole candidates and 2 neutron star black hole candidates and 0 binary neutron star candidates. So this is a significant increase in the number of binary black hole detections that we've had since from prior observing runs. And we also have, next please. We also have one published binary black hole detection, which was that special event that I was talking to you about earlier, GW250114. So that will be featured in the GWTC5 catalog. Next slide, please. So we can take a look at our search sensitivity now, and we use injection studies to determine our sensitivity of our searches across the CBC parameter space. And CBC just stands for compact binary coalescence. So those binary black hole mergers, neutron star black hole mergers, and binary neutron star mergers, and those are the types of injections that we use. And injections are just simulated signals, which we add to the O4a data, and then we analyze them to see how many we recover. We take the fraction of the injections recovered and compute the volume time sensitivity, which is that quantity VT shown on the right side of the plot. And we do this by taking the fraction of injections recovered, computing the volume time sensitivity by multiplying the astrophysical co-moving volume V, in which the sources were injected, with the fraction of recovered injections. And then we multiply that by the duration of the search, or this T, to get the space-time volume sensitivity. And here we're showing the results for any pipeline. So we have multiple pipelines which analyze our data and produce candidates, but here we're combining those results. And this is featured in figure 1 of our paper. And this shows us the sensitive hypervolume VT for injections found by at least one search pipeline, which we can also call any because it can be from any search pipeline. On the x-axis is the primary mass, or mass 1. This is the larger mass in the system. On the y-axis is the secondary mass, which is the smaller mass. On the diagonal is the mass ratio line. So these are equal masses, Q equals 1. And then these diagonal or these sort of curved lines represent the M-chirp values. And we can see on the color bar that a lighter color indicates a more sensitive region, and also a higher number indicates a more sensitive region. And we analyze these injections at different points in the parameter space, which is why we have very specific points listed here. And you can see that we test for sensitivities from about 1.5 to all the way up to about 100 in solar masses. And we see that we're more sensitive to things that are higher in mass, and that's because we are able to detect those at farther distances. So it's harder to detect smaller things because they're normally quieter, and then we can't detect them out as far in space. But for heavy binary black holes, for example, it'll be easier to detect those, and we can see that in the top right. So this shows us, if we compare this to the O3b results, that we've actually nearly doubled our sensitivity compared to prior observing runs, even though we observed for about 1.4 times as long as O3b. So it's a significant improvement, and this is due mostly to detector improvements, but also to search method improvements. So this is fantastic to see. Okay, next slide, please. Thanks.
Thank you very much, Amanda. My name is Lucy Thomas, and I'm a postdoctoral researcher at the LIGO lab at Caltech. And I'm going to be talking in a bit more detail about the source properties of the events that Amanda's just given us such a nice overview of. So next slide, please. So we're showing here source properties for the 86 events for which there was a false alarm rate of less than 1 per year, and also a probability of being astrophysical of greater than 0.5, which out of those 126 events that Amanda just described, there are 86 of those. And in the paper, we show the principal parameters here represented in these big family photo plots and tables. So here, this big plot is just a summary, but the full posteriors are available for download in the Gravitational-Wave Open Science Center data release. And there were up to 4 waveforms used in the analysis for binary black hole events. These 4 waveform models are IMR phenom XPHM spin Taylor, SUB NR V5PHM, NR SIR7 DQ4, and IMR phenom X04a. And I should say that for every binary black hole event, the first 2 of these analysis was run. For the events which fit into the validity range of NR7DQ4, this analysis was also run. And then for events that show possible evidence of asymmetric masses or possibly spin precession, we also do analyses with IMR phenom X04a. And then the results that we show in the majority of the paper, unless it's otherwise stated, are a mixture of the samples for all of these waveform models for each event which were run. And also in this plot, you can see that for the first time in a gravitational wave transient catalog, we're also showing underneath the mixed samples, which are the colored, shapes underneath. We're also showing in white the results that are reweighted to the inferred population from GWTC-4. And Bilby and the dynasty sampler were used for all of this parameter estimation. Next slide, please. So if we take a look at the masses of these sources, in GWTC4, we have new events which may have both higher and also lower total masses than were previously reported in GWTC 3.0. And this plot is showing a summary of that. So you can see the total mass in the source frame of the system of the systems on the x-axis, and then the mass ratio where 1 is equal mass on the y-axis. And GW231123, as Amanda said, is likely the heaviest event that we report. And you can see on the right-hand side, that red dashed blob is GW231123. Again, I should say that these are all the mixed samples. We also have 4 events that may have produced an intermediate mass black hole remnant, where the final mass is greater than 100 at 90% probability. And we also have 4 events that have some posterior probability of having a component in the lower mass gap. So this is where their secondary mass, M2, is possibly between 3 and 5 solar masses. And I should just add to this that we don't have any events in this catalog for which the primary mass is likely to lie in this gap. So in the plot, we're just highlighting a few of these interesting candidates in colored and dashed lines to show events that are sort of highlighted with interesting total masses or mass ratios. Next slide, please. If we consider the spins of the source, so the bulk of the observations in GWTC4 are consistent with having 0 effective aligned spin. So the aligned spin, which is chi-effective on the y-axis of this plot, goes from 1, which is saying that the maximum possible amount of spin is pointing in the same direction as the orbital angular momentum of the system, down to -1, which is essentially that the maximum possible amount of spin is pointing in the opposite direction to the orbital angular momentum. And you can see in the plot that for the bulk of the systems that we have, the posterior blobs are consistent with an effective spin of 0. We have 16 candidates that are likely positive aligned spin, that their chi-effective is greater than 0 at 90% probability. And we also have 3 candidates for which the chi-effective is likely negative, so it's below 0 at 90% probability. And we've highlighted on the plot some notable cases, but just to point out a few of my favorites, we have 231028, which Amanda said was the highest spinning event in our catalog. 231118 and 231123. All 3 of these are likely positive spin events. And then we also have 230518, which is one of our 2 neutron star black hole candidates for which the spin was likely negative. And you can see these events as well as a couple of others highlighted in this plot. Next slide, please. And then if we think about the orientation of the spins of those of those gravitational wave events, so spin orientation is generally fully measured as it was with GWTC 3.0. The posteriors are normally quite wide. Here we're showing spin disks for a number of candidates where the spins are interesting or well constrained. So the way to read these plots is that the spin magnitude, how large the spin of the neutron star or black hole is the radial direction. So if there is more color towards the outside of the spin disk, that means that there's more posterior probability that the spin was large. And then the direction from top to bottom is at what angle the spin was pointing. So top is it was aligned with the orbital angular momentum. 90 degrees is that it was completely perpendicular to the orbital angular momentum, and 180 degrees it was in the opposite direction. So some outstanding events include GW230518, which you can see in the top left in gray, for which the primary spin is really well constrained to be very small. We also have 231114, which is on the right-hand side in purple, which again, the primary spin is constrained to be small. And also GW231226, which is the bottom right in orange, where both the primary and secondary spin are constrained so that they're likely in the orbital plane rather than aligned or misaligned with it. And there's a few more interesting examples shown in the plot as well. Next slide, please. And then we'll consider the effective precession spin. So this parameter goes between 0, where there is no spin precession at all, to 1, which is where the maximum possible amount of spin is lying in the orbital plane. And spin precession is a possible marker that if there is evidence of large spin precession, this is a possible marker that the binary may have been formed in a dynamic environment, in a dense environment. So we are showing here effective precession spin posteriors for selected events where these posteriors are significantly different from the prior. So either where they're well constrained or where there's evidence that there is spin precession. So some outstanding events in this plot include 230814, where you can see that because the SNR of this event was quite high, the effective precession spin is well constrained. That's the posterior exactly in the middle in this purple color. Also, 231114 is well constrained to have a small effective precession spin. And then we have 231123, for which the effective precession spin is constrained to be high. Next slide, please. We also consider events which show different results when they're analyzed with different waveform models. So in this plot here, we are presenting results for the 5 most significant examples where the results with different waveform models are the most different. And the most notable example in this plot is GW231123, where you can see that for all of the 4 different analyses which were done on this event, shown by the different colors and line styles, there are noticeably different results for the total mass, the source frame total mass, the mass ratio, the effective aligned spin, and the effective precession spin. But there are also some other notable examples as well shown in this plot. Next slide. And finally, to check that we're not incurring additional systematics by missing signal content in our compact binary coalescence waveform models, we also produce reconstructions with 2 minimally modeled pipelines used to reconstruct the candidates. So we use, for these minimally modeled pipelines, we use Bayes wave, and then we use CWB coherent wave burst in 2 different configurations, CWB2G and CWB-BBH. And I should say that Bayes wave and CWB2G are designed for very generic transients, whereas CWB-BBH is optimized for binary black hole transients. And we compute the overlap between these off-source reconstructions and then the on-source actual signal. And in these plots, we can show that the overlaps lie along this line, diagonal line of equality. So we see no significant differences between the on-source and off-source reconstructions, which is suggesting that we're not missing any significant amount of signal content in our waveform models, so we're not incurring additional systematics.
Well, thank you very much, Lucy and Amanda, for giving us that comprehensive overview of the GWTC 4.0 catalog and the results therein. So I'm just going to leave you with this conclusion slide, just as a quick reminder that we had 128 new candidates, where we got 86 with parameter estimation, and we have a number of particularly exceptional events in there, some of which got their own exceptional event papers, including 231123 and 230814, alongside the catalogue. And just quickly before I open the floor up to questions from the audience, I wanted to take a moment to remember that the amount of work which it takes to put together one of these catalogues requires far more than just the small number of us who are here on the webinar today to talk to you. So the parameter estimation itself required a team of over 60 people, and the search component, a very similar number of additional people to put all of this work together. And that is in addition to all of the work which is required right across the collaboration from hundreds, thousands of scientists spread around the world, many of whom are early career researchers who put vast amounts of effort into the work which we've managed to distill now to just over 20 minutes, and to this really quite large and detailed paper which we're describing. However, I think it's now makes good sense to move on to questions. So we have 2 different options for how we take questions. You're welcome to either type questions into the questions and answer, the Q&A section, which you should be able to access via the Zoom controls. Or if you want to ask your question verbally, you can raise your hand, and then we will hopefully get some assistance with managing the questions section of the webinar. We have a whole panel of people to try and answer those questions. So yeah, please do feel free to enter your questions. or use your hand. Let's give everybody a moment. And okay, so we have our first question which has come in, which is that a recent paper suggests that GW231123 could be magnified by a gravitational lens, which would reduce its true mass. What's the LVK's perspective on this claim, and have you done your own lensing analysis of 231123? And how would you confirm or refute that this event is actually lensed? Now, unfortunately, on the panel, I don't think we have any of our LVK lensing specialists. I don't know, Lucy, would you like to take this as a parameter estimation adjacent question?
Yeah, I can have a go. I believe that there are ongoing analyses of 231123 with respect to lensing within the collaboration, although I can't speak as to the current state of any results. And as a non-lensing expert, from my perspective, I think a possible way to make a statement on any claims about 231123 with lensing are to look at potential Bayes factors between two analyses with lensing and not lensing, and statistical methods such as that.
I don't think I have anything greatly to add to that, except that I know that efforts are ongoing at looking at these different signal hypotheses for 231123, which is clearly a particularly exciting event. I don't know if anybody else on the panel wants to weigh in on this question. So somebody has reminded me, thank you, Tom, that there is indeed an LVK paper. There is indeed an LVK paper where somebody looked at this, which I think appeared on the archive at the end of 2025. So we have, this is the GWTC-4 lensing paper. So we have started to look at lensing scenarios for events in GWTC-4. So yeah, this is something which, again, I don't know whether the lensing team are intending to do their own webinar at some point in the future. I suspect that they probably will be to accompany that paper. Are there any other questions? If anybody has anything, please do feel free to raise a hand or type in the question and answer box. I will give everybody just a moment or two longer. Great. Okay, so we've had one question, which is, what is your sense about the spin being distributed around zero? This kind of feels like a parameter estimation question as well. Lucy, you were talking about spin. Do you want to take this initially as well?
Sure. Yes, I'm going to take your question to be that about the effective distributions being spread roughly around zero. And I guess I'll sort of answer this with two potential points. The first being that because of the way that our priors are constructed to be isotropic in spins, that if your spin is unconstrained, if you're not getting a lot of spin information from your gravitational wave signal, then if your posterior is prior dominated, then it will naturally look as if your chi effective is centered about zero. So one answer to this question may just be that it is difficult to constrain spins, and so they appear to be clustered around zero. And the other answer is that maybe this is in fact astrophysical, and in which case it would seem that the binary black holes don't really have they either have small spin, and so chi effective is zero, or that the chi effective is not preferentially aligned particularly or misaligned particularly with the orbital angular momentum.
Thanks, Lucy. Does anybody else from the panel want to weigh in on that? Okay, the next question which we had is, do you know how the forecast of detections for BNS, what the forecast for detections of BNS sources, that's binary neutron star sources, is in the upcoming stages of the O4 campaign, or for O5 and beyond? I wonder, Cody, is this maybe one for you on the searches side?
This is not something I know off the top of my head, as this is more a rates and populations question, which I don't think we have a rates and pop expert here, unfortunately. But we do, I'll advertise, I'll put this in the chat. We do try to keep an estimate somewhat updated on our observing capabilities. So our user guide for which is primarily where you'll find information about low latency notices and that sort of thing. I don't off the top of my head know the last time this was updated, but I know that there's chatter about updating this fairly frequently. A couple times a year, it seems like. Yes.
I think the chat is only accessible by hosts and panelists, so you'll have to paste that in, type answer on the Q&A.
Thank you very much. I will type that in there. So sorry I can't give you something more direct, but that is at least our official documentation. And if it hasn't been updated in a while, I know there is constantly chatter about this, and so I would expect it to be updated before our next run.
I think the only thing which I would add to this is just a little bit of clarification on what the O4 campaign looks like. So the O4 observing has now concluded. So O4 observing ran from May 2023 through to November 2025. So we have completed data collection over that period, but of course we've only so far completed and published the analysis of O4a, what we're talking about today. So we are expecting to have two more sets of catalogs come out of O4, so O4b, which is the middle part of that observing run, and then O4c will both get GWTC-5 and GWTC-6. So there are many results still to look forward to out of all of that, although as we haven't completed the analysis, I don't have any more exciting information to share just at the moment about what might be in those. So the next question which we've got is, does GWTC 4.0 improve on polarization constraints compared to O3? That's not the question which I think I know the answer to. Is there anybody on the panel who is able to? Yeah, I'm not sure. I think this is maybe something which people are still looking into. It's certainly not something which we've got in the results paper itself. So depending which polarization constraints you're thinking of exactly, that might be something which is still to come from one of the other analyses. I'm now going to switch. I've just seen that we have a raised hand from Francesco. So Francesco, if you want to go ahead and ask your question. Francesco, if you're asking your question, I'm afraid you're muted. Casey, I don't know if this is something which we need a bit of help with.
It looks like, apologies, Francesco is able to unmute. If you're having technical issues on your end, Francesco, would you mind putting your follow-up question in?
Sorry, I'm sorry. That must be an accidental. I will load the end. There's no question. Thank you. Sorry.
No problem. Okay, so the next question which we've got on the Q&A is it just a low mass that indicates that emerging component is a neutron star and not a black hole? Or is there some additional waveform signature that can also help distinguish neutron stars from black holes? I'm going to, Amanda, do you fancy taking this one?
Yeah, I think it's mostly which template matches well with the signal when we're doing, for example, match filtering searches. So our templates are modeled with the given waveforms and informed by general relativity. So we expect like the waveform for a neutron star black hole to look a certain way. not just in the masses, but it will also maybe be a different duration in the waveforms, since the masses could be smaller of the components. And yeah, so we perform match filtering, we get this template. The template has some prior estimates of the masses and gives us some information, and then that goes on to parameter estimation to fully analyze those masses and see if it's a neutron star black hole, something in the mass gap, or something else. I think that's the most I know about waveforms, but that's how we would detect a neutron star black hole versus like a binary black hole. Maybe Cody has more to add.
Yeah, Cody, go ahead.
Yeah, I unfortunately don't have all of the details for the event papers in front of me, but I can say in general, to zeroth order, the first thing we look at is just the masses. So when we're doing our searches, we look for a preset bank, more or less, or most of the pipelines do. There is an exception to this, but we more or less look at a preset bank of waveforms, where we have the input like mass and spin, et cetera, that we know what was made with the bank. And when we do that zeroth order search and we're just looking for, does it match one of these millions of waveforms in our bank, we assume that they're basically point particles. So we assume that there's not going to be any tidal deformability or any matter effects in them. But then additional follow-up is done by parameter estimation. And so I don't know if Lucy can weigh in on what happened with these, where we do add extra parameters to see, can we measure anything about tidal deformability? I think, if I remember correctly, that it's fairly difficult to measure. So I think there's at least one candidate from O3, I want to say, where there is something that has a mass that we don't understand, and it wasn't loud enough for us to be able to really distinguish, is this a neutron star or is this a black hole? But I don't think these neutron star black hole binaries had that issue. So sorry if that's an unsatisfying question. To recap, zeroth order is we just look at the masses, and then PE does additional follow-up to see if there's more behavior that can be explained by there being matter. All right, I'll shut up for Lucy now.
Yeah, I just wanted to add, as Cody and Amanda alluded to, that then the search results are then fed to parameter estimation, and we do use these waveform models that have the effects of tidal deformability, so the neutron stars being stretched and squished as they're orbiting and merging built into them. But as Cody said, this is a fairly subdominant effect in the gravitational wave signals that we observe, especially compared to the effects of the masses and even the spins of the objects. So it's really difficult to constrain these tidal deformabilities if you don't have a very loud signal. I think there is maybe only one exception to this, which is that for GW170817 we were able to make to constrain the tidal deformability, which is how we got such good results for 170817 on equations of state measurements and things like that. But apart from this one event, it's in general very difficult to measure. So for the neutron star black holes in this catalog, we did run parameter estimation with waveform models that include tidal deformability, but the results are unconstrained, so we're not able to say anything about the matter effects in the events.
Thanks, Lucy. That was way better said and way more informative than what I said. I just wanted to add for context, when Lucy said, that it's subdominant but we could see it for 170817, which was the first binary neutron star we saw. That was at the time the loudest signal we had seen. I don't remember the SNR off the top of my head. It's no longer the loudest, but I believe it's still in the top 5 loudest. Or if it's not, it's just outside that list, out of the 218. So you really do have to get a fantastically loud signal with a neutron star to pull these details out.
Thanks everybody for that a useful discussion, I think, on binary neutron star and neutron star waveforms. The next question which we've got is, with the large number of gravitational wave events, is there a way of determining the effect of natural events versus artificial events? of parameters which would be used. So I think this is a question about effectively about data quality. So Zach, I don't know if you want to take this one.
Sure. I think actually this question was interesting to me. So I did a quick Google, and I think maybe the parenthetical there is something in the universe using a gravitational wave as a form of uh, using it as a power source. Maybe Cody, do you want to chat about this one together? But I mean, I think like maybe on the data quality side of thing, like if there's a something to be said about that, right? Like the way we distinguish real from fake in general, right? Be it from produced elsewhere in the universe, from something that's not just emerging compact system, or something produced here on Earth by our noise. It's really the way we distinguish it is the same, right? And that's that we've talked a lot about these waveforms that we use, and we use Einstein 100 years later in order to determine what the signals that we are looking for should look like, what the masses look like, what the waveform should appear like in the detector, and that's what we look for. And the way we distinguish signals from noise, and wherever that noise category appears from, is the way is the same. And our search methods are really good at only identifying the stuff that looks like actual naturally produced gravitational waves, and throwing away the stuff that looks fake.
Yeah, Zach covered 95% of what I was going to say. So great explanation, Zach. I was just going to try to drive home the point that these signal morphologies really are driven by the system that generates them. And even in compact binaries, binary black holes, for example, the masses, say you have the exact same spins, and everything else is the same. The masses really don't have to vary that much for the overlap between the signals from slightly different massive systems to start to diverge. And so even when you're looking at a system that it's still two black holes, maybe they're 10% more massive or something like that, but otherwise very similar system, you're still not going to ring up the same. It's still going to look very distinct from each other. And so when you extend that to looking at something massively different, where gravitational wave signature from something like a faster than light drive or something like that is going to look drastically different than these in spirals that we get from compact binary mergers. But that's a really cool question, and I will say I think people are thinking about this sort of thing. I don't know about in the collaboration, but I just want to call out that that's a neat question.
Yeah, thanks very much, both. I realize I slightly misinterpreted the question, so thanks, Zach and Cody, for saving me and picking up on what Mark meant there in the question. So unless anybody else on the panel wants to weigh in on this, I think we can move on to the next question then, which is, with these detections, are you coordinating with any other observatories? So I can very quickly give an answer on this, and then I see Cody's got a hand up with the simply the answer to this is yes, that we publish information about our gravitational wave candidates almost live, so as quickly as we can after we've detected them with the LIGO. Well, in the case of this catalog, the LIGO detectors, and later on in O4, LIGO, Virgo, and KAGRA. So when we make a detection, that is made publicly available, and then various observatories around the world do pick up on those the information which we've put out in order to then follow up some of the observations. I see Cody is typing an answer, but Cody, if you want to speak, that's fine as well.
Yeah, I just figured I would this is one of the hats that I wear, is working on disseminating these sorts of notices. So I just thought I would advertise another link. Hopefully it showed up in there. So this is to the EM Follow user guide that I dropped earlier, but the main page of it. And just want to advertise, if anyone is on this call that's not affiliated with a university or a group, anybody can receive these notices. You could set it up to have it streamed to your computer. absolutely no charge, and all the information is there. So I know there's amateur astronomers that like to do that. And there's also contact information on that page. If you have any questions or get stuck, please feel free to reach out and ask, and I'd love to help you.
Great, thanks, Cody. So I guess we can move on to the next question, which is a little bit related, which is, do you have any ongoing multi-messenger analysis for the O4 run, or was this already handled on a real-time basis with the GCN alerts and follow-ups? So again, I can very quickly give an answer to this, but if any of the other panelists are more involved with the EM analyses, the answer is yes. There was lots of work done on a real-time basis or near real-time basis, as Cody says, with GCN notices. But we do have various offline analyses, particularly looking at GRB events is one of the major examples of this. But we look at coincidence between gravitational wave events and potential GRB events. That's mostly done offline. So the results from that are likely to take some time to appear, just because we've got really quite a lot of analysis to do for that. And another area, again, where we look at multi-messenger analyses over a longer time basis is with high energy neutrinos between the gravitational wave signal and high energy neutrinos. I don't know if anybody else has anything to add to that. All right, but thank you for the question. Then I think we're getting quite close to the end of the questions now. The next question which I got is there a way to find the mass information from events in O4b and O4c, or a timeline for when that will be available? So I think at present that information is not currently available. So to give you some idea of why we need some time to do this, the process which we use to get the accurate measures of M1 and M2, as well as the remnant mass M final from our data, is relatively slow. It is this parameter estimation process which Lucy talked about during her part of the talk. So we have completed that for GWTC-4, so for the O4a, the first part of the O4 observing run. But we will need to wait until results are completed for O4b and O4c. Now, those analyses are ongoing, but they do take a little bit of time for us to get through. So I know O4b the analysis is proceeding at pace, but I don't know I can't remember exactly what the planned publication date for those is, but I think you can find the date when that data is made public, which is when I would expect to see results. Yeah, as Cody says, I think the GWTC-6, so the part of O4c, we're expecting to see by the end of this calendar year. So GWTC-5 is somewhere in between, but I'm afraid I can't remember off the top of my head exactly what those dates are. Lucy says it's around May or June, so in a bit less than half a year's time. Then I think we can move on to the final question, which is maybe one which we can have the panelists muse on slightly, which is, how surprising is it that there was no BNS detection during O4? I'm going to take this question as being during O4a, since that's principally what we're here to talk about, because we don't have the full final offline results from O4b or O4c yet. I think if we just skip back to an earlier slide, we can see the slide showing what we anticipated. So our observing scenario, so as Amanda introduced this, the observing scenario which we had before we started taking data in O4, so this slide was produced in 2023, just before we started observing. We did have 0 binary neutron stars as one of the things which we expected might be one of the observing scenarios, one of the plausible scenarios. We had rather hoped that number might go all the way up to 62. And clearly we ended up very much on the left-hand side of that error bar than the right-hand side. I don't know if anybody else wants to weigh in on. So this is in a sense kind of a populations question rather than a directly parameter estimation question. But yeah, Zach, go ahead.
Yeah, I mean, it definitely is a populations question, and I'm not qualified to speak to that. But, I tend to think about this from a detector perspective as well. And like the way in which we engage with the things that we observe is so fleeting in a way. There are times when we are not able to have our observatories running for a variety of reasons, environmental or even planned maintenance that we coordinate between detectors. And that's kind of the nature of what it is that we do. If we happen to not be able to take data when a BNS occurs, we can't go back and get it, right? So this is a big disappointment, I'm sure, to all of us, right? Like we all want to see something like 170817 again. We all jump when we get an alert and check the mass parameters, right? But a lot of it is just, I don't want to say poor luck, but that could absolutely be a contributing factor here, that we just weren't able to catch an event that occurred. And of course, our multi-messenger counterparts would catch things like that too. But that's just to say that there are extenuating circumstances that make this all the more challenging.
Cody, I noticed you had a hand up.
Yeah, I waffled on it, but I'll say what I was gonna say. Yeah, I 100% agree with Zach. I also my expertise is not in rates and pop, so I will leave more definitive answer to other experts. But I will say Poisson statistics are weird. Um, so it's disappointing. Um, and I've heard rumblings that so this is not an official LVK position, but I've kind of gotten the vibe that the further we get, the more it seems like we got really lucky with 170817, like fantastically lucky to get that. Which is again, Poisson statistics. And you can even see it. We have a slide that shows, to illustrate how weird Poisson statistics are. We have a slide that shows how many candidates we saw and how often over the run. And on average, we'd see one every 3 days, but there was once or twice that we'd go close to a week without seeing one, and then we'd see there's a couple times we saw three in a single day. And so and this is with binary black holes where we expect to see one every 3 days. So with binary neutron stars, where we expect to see fewer, even though the rate is expected to be higher universally, our range is substantially low enough for BNSs that we expect to see far fewer of them than BBHs at this sensitivity. You could imagine that if it's maybe once every 6 months, I'm just making that number up, but just to illustrate a point, if it's once every 6 months, then you might go 18 months without seeing one regularly, and then see one or two in a 6-month period or something like that. So it's disappointing. And I can't say this with 100% confidence, but the vibe I have gotten is it's disappointing, but it's not yet alarming.
Yeah, I think that's right. And I think it is important to remember that the sensitivity of the detector really is much higher to these binary black hole signals rather than binary neutron star signals. So whilst between O2, when we made the detection of 170817, and O4, the sensitivity of the detector has improved substantially. I mean, that the amount of extra volume of space which it's sensitive to for binary neutron stars is significant, but what we really do expect is to see a lot more binary black holes, just because we are sensitive to such a large fraction, a much larger fraction of the universe in comparison to what we are with binary neutron stars. And I think perhaps not surprising, as I said at the beginning, it is 0 was a number which we thought was a distinct possibility. It was not the number perhaps which in our heart of hearts we wanted, but hopefully going forwards we will start to see these, but it just reminds us how exciting binary black holes are to analyze when we have so many of them instead. I don't know if anybody wants to yeah, as our question comments, 62 would have been a better surprise scientifically. I think 62 would have been exciting challenge for us to analyze.
I don't know, by the 62nd, I might have gotten a little annoyed.
I'm sure our colleagues working on cosmological analysis would have been thrilled. Okay, I think we have pretty much exhausted our questions. So unless anybody on the panel has anything else which they want to add, I'd just like to thank everybody who came along today. I'm going to quickly flip back to my advert for next week. So please do tune in again on the 19th of February, where we will be discussing the methods which we use, the statistical and search methods, which we used to produce the results which we've had the pleasure to talk to you about today. I'd like to thank everybody on the panel. So that's Amanda, Lucy, Cody, and Zach, as well as Leo for introducing us, and a massive thanks to Casey Sloan for making sure that the webinar went ahead technically and worked as smoothly as it has. And thank you to everybody who has come along today to hear us talk about GWTC4. We hope we'll see you next week, and we look forward to talking to you more about the results from GWTC5 from O4b at some point in the hopefully not too distant future as well. So thank you very much.